It's 8 o'clock, so we'll start the Monday morning lecture for June 14th. We'll start out with a simple observation. If we let m be a positive number, we can easily determine the value of this expression. So we have m to the raised to the exponent 1 over m, and then this is raised to the exponent m to the exponent 1 over m, and that is raised to the exponent of m to the exponent 1 over m, and so on. The three dots indicate that this pattern goes on forever. So if this is equal to some finite number, let's just say that r is equal to that number, m to the 1 over m raised to the m to the 1 over m raised to the m to the 1 over m, and so on. Okay, but notice that after the first term, the following exponents is exactly the same as what r is, since it goes on forever. So we note that r is equal to m to the 1 over m raised to the exponent r. And then we just observe that when r equals m, just replace r with m, we get m equals m to the 1 over m raised to the power m. And then using properties of exponents, m to the 1 over m to the m, that's equal to m to the m times 1 over m, but m divided by m is 1. And we get a true equation. So this simplifies to the number n. We'll be using this fact a little bit later in a specific case. For the next problem, let m be a positive number, let b be a positive number that is not equal to 1, and then we'll find values of x that are positive that solve this equation. So find x greater than 0 such that x to the m equals b to the x. Well, I'm just going to write down what one of the values of x could be. So if x is equal to the mth root of b raised to the exponent, which is the mth root of b, which is raised to the exponent, the mth root of b, which is raised to the mth root of b, and so on. Since it's an infinite process, we put the three dots to indicate that this goes on forever. Using properties of exponents, or also a property of radicals, the mth root of something, so the something is b raised to this exponent. So I'll just put a few of those in. The mth root of b raised to the mth root of B, and so on. But the nth root of something is just that something raised to the exponent 1 over m. Okay, so notice that inside the brackets, the exponent on b is the same as what is equal to x. So we can just write, I'll write it over here, x is equal to b to the x to the 1 over m. And then using another property of exponents, if I raise both sides of this equation to the exponent m, I'll get x to the m equals b to the x. So this is the equation that we're solving. So I've shown by illustration that if x is equal to this expression, then it is a solution to that equation. Well, there's another equation, or another solution, I should say. So this time I'm just going to pick x to be m times the base b logarithm of m times the base b logarithm of m times the base b logarithm of m times the base b logarithm, and so on. So the same pattern goes on forever. So we put the 3 dots. Okay, using a property of logarithms, if I have m times the base b logarithm of something, I can write this as the base b logarithm of that something. So inside the brackets, I'll put m times log base b of m times log base b of m times log base b, and so on. And then the exponent on the argument is the number m. In the previous step, m was the coefficient of the base b logarithm, but using a property of logarithms, we can move m to the position of the exponent on the argument. And then using the definition of a logarithm, if x is equal to the base b logarithm of something, then b to the x, b raised to the power x, is equal to whatever that something is. Something this is what we have over here for the argument raised to the power m. But notice that the argument is what x is defined to be. So in the next step, I'll just write x is equal to log base b of x to the m. And then using properties or the definition of the logarithm, b raised to the power x is equal to x to the m. So this, once again, this is the equation that we're solving. So there are 2 solutions to that equation where x is greater than 0. Okay, on the next page, so once again, we let m be a positive number and we let b be a positive number that's not equal to 1. And so I'll show here that if b if the base number b is equal to the number e raised to the exponent m divided by e, then the equation x to the m equals b to the x has exactly one positive solution. Well, if we just replace b with e to the m over e, then we get this equation, x to the m equals the base number e to the m over e raised to the power x. And we observe that this equation is solved when x equals e. Because if we substitute, replace x with e, we get e to the m on the left-hand side. And on the right-hand side, we get e to the m divided by e raised to the exponent e. But using properties of exponents, e to the m over e to the exponent e, we multiply the exponents and we just get e to the m. Okay, but we want to show that x equals e is the only positive solution. So remember, in general, if we have one of the solutions is x equals the mth root of b raised to the mth root of b, and so on. But if we replace b with e to the m over e, then we get x is equal to the mth root of e to the m over e to the mth root of e to the m over e to the mth root of e to the m over e, and so on. Sort of looks sloppy. But then using the definition of the radical, we can rewrite this. So, because the mth root of something is equal to that something to the power 1 over m. So inside the brackets, we have e to the m over e, and then the exponent m to the mth root of e to the m over e, and so on. And this is all raised to the exponent 1 over m. So when we apply properties of exponents, we can multiply this exponent 1 over m times the exponent m over e. So we get x equals e to the 1 over e raised to that infinite exponent again. But if I repeat the process on that exponent that I did in the previous step, then what I'm going to get is e to the 1 over e raised to e to the 1 over e raised to the exponent e to the 1 over e, and so on. And as we saw earlier, in the special case where m is greater than 0, this simplifies to e. Okay, so the purpose of this was just to show that when b is equal to m over e, then this equation has one solution. So this particular solution, x, is equal to e, which is the same number that we observed is a solution. Okay, what we want to do not, in the next step is to show that the other solution for x is also equal to e. So this one, we use the other equation, x equals m times log base b of m times log base b of m times log base b, and so on. But this time we replace b with the base number e to the m over e. So we have m times log base e to the m over e. This time I'm going to do this a little bit differently. Notice that this argument is the same as what x is, so I'm just going to write this as x equals m times the base e to the m over e logarithm of x. But if we continue this process, well, in the next step, I'm going to rewrite this as the logarithm with base e to the m over e equal to x to the m. And then using properties of exponents, or the definition of the logarithm, we get e to the m over e to the x equals this argument x to the m. And this is true when x equals e. Okay, so the point of this little exercise was to show that when the base number b is e to the m over e, the two solutions for this equation are the same number. Okay, in the next step, the goal here is to show that if b is less than e to the m over e, then this equation has two positive solutions. But I need to amend this. This has to be done in two cases. So we're going to replace, in this case, we're going to require that the number b is between 1 and e to the m over e instead of just positive. Okay, so one of the solutions, as we have seen, is x equals the mth root of b to the mth root of b, and so on. And this is equal to b raised to the exponent, which is the mth root of b raised to the mth root of b, and so on. But we have an outer exponent of 1 over m. Okay, and so if b is less than e to the m over e, then this expression is less than e to the m over e to the x to the 1 over m. And when I apply properties of exponents, This will simplify to e to the 1 over e to the x. Well, if I do the same process again with this x, I'm going to get x is less than e to the 1 over e raised to the exponent e to the 1 over e to the x, and then apply the same process to this exponent x. And if we keep doing that forever, we get x is less than e to the 1 over e raised to the exponent e to the 1 over e, and so on. But as we saw earlier, this simplifies to e. So this time, x is less than e. That's one of the positive solutions. Okay, this time we'll take a look at the other solution that has the form x equals m times log base b of m times log base b of m times log base b, and so on. Okay, one of the things about logarithms, if you take the a base b logarithm of something, and then if you increase the size of the base but leave the argument the same, the number gets smaller. So m times log base b of all of this is greater than m times log base e to the m over e of that expression. This expression that's the argument is the same as what x is. But then if we do the same process on this x, then this expression is going to be greater than m times the base e to the m over e logarithm of m times the base e to the m over e logarithm, and so on. But we saw earlier that this logarithm is equal to e. So this time x is greater than e. The other solution, x is less than e, and the second solution, x is greater than e. Okay, that's all we have time for today. So next time, we'll look at something else.